Hi, today I'm going to introduce the Tate construction. Tate construction will be defined for an object with a g-action as the cofibre of the norm map. I will identify the Tate construction for finite groups, and I will also explain how the Tate construction can be viewed as a deviation from Poncaré duality. Hi, I'm Thomas Nikolaus from Mathematics Münster. And the Tate construction will be something related to groups. So let's talk about kind of group we are thinking about here, and what we want to place ourselves in the setup is that, G is a group object in the infinity category spaces with Cartesian product, i.e. a group like E1 space. So an example would be given by just an ordinary topological group, or say just even a discrete group. You can just consider it as a space with a discrete topology, and that gives you a group object. Or actually a topological group, and I guess I haven't said this in my video about E1 algebras, but every such group object can in fact be modeled or is of the form given by a topological group, actually. So if you want, you can just for simplicity or for constructions assume G is an actual group object, but the correct generality is the one of group like E1 spaces. So in that case we have the bar construction BG, which is a space, right? And again, this was covered in my video about EN algebras. This is an equivalence between group like E1 spaces and pointed connected spaces. So every pointed connected space is of the form BG for a G some group object like this. And then of course we can look at the category of, so if the C is any infinity category, we have the functor category from functors BG to C, and that is what we mean by objects in C with G action. Okay, and here's a construction. So for G, such a group object, as before, we consider the underlying space G as an object in spaces to the BG cross G. In other words, a space with an action by G cross G by letting G cross G act on G as follows. We just want to say that, we just act from the left and the right. So G comma H times X is just defined to be G X H to the minus 1. And of course, in order to get this actually a functor from BG cross G to spaces, you either have to write that down cleverly in terms of the bar construction of G, or actually G itself and a functor, depending on what exactly you do, or you just refer to the thing I said before, that actually we can, without lots of generality, assume that G is itself a topological group, and then you get that. This doesn't quite reflect the full functoriality of the construction, but it's good enough for what we do today. Okay, and now once we have done this construction, we can give the following definition, and this is in this form due to John Klein. And it says we define a spectrum DG, which is going to be a spectrum with a G action called the dualizing spectrum of G as follows. So what we do is we have this group object G, where G acts on itself from G cross G acts on itself. So if we take the suspension spectrum of G, then this still has an action by G cross G. And what we're going to do is we're going to take the homotopy fixed points for G cross 1. Right, by this I just mean the group G as included into G cross G from the left. So in other words, G acts on the left from this, and we take the homotopy fixed points for this action. And this has with its remaining right G action. With its remaining G equals 1 cross G action. Right, if you have something which has a G cross G action, then after taking homotopy fixed points, you have a residual action by 1 cross G. One way to see that highly coherently is just to observe that in the category of objects with an action by G cross 1, you have the endomorphisms by 1 cross G. And taking homotopy fixed point is a functor. So you get that remaining action. Okay, so, and that is what we mean by the dualizing spectrum of G. That's the definition. And most of today's talk is about justifying the name dualizing spectrum. And in the end, we'll also see that one can also characterize this dualizing spectrum by a universal property. But for the moment, it's just this specifically defined spectrum. And let me go through some examples to begin with. Examples. So the first case is assume that G is finite group. Then let's try to work out what the dualizing spectrum is. So what we have then is, well, then of course the suspension spectrum of G is just the direct sum of copies of the sphere where G ranges over all elements in G. So that is what the suspension spectrum of a finite set is, right? It's just the sum of the elements in that set over the sphere spectrum. And I guess, so now what we have to compute in order to compute the dualizing spectrum is we have to compute the homotopy fixed points for G acting on the indexing set. The action here is such that G exactly only acts on the indexing set. And the claim is that this is actually equivalent just to a single copy of the sphere. And this is similar to the fact, if you think about the ordinary land analog, there you would have that replace the sphere by, say, the integers. Then you would just have a copy, I mean, this would just be the regular representation of G. And if you just then take the fixed points, the invariance of the regular representation, that would just be a single copy of the integers. Right? And the point is, what is the morphism? The morphism is just, I mean, you have a forgetful map from the homotopy fixed points down to the spectrum itself, and then I can just project to the, say, first component. Right, so it doesn't matter. So the way somehow this sits inside of here is somehow it sits diagonally inside of here. But the canonical map goes this direction. And the claim is this is an equivalence. And how does one see that? The idea is to reduce it somehow to the same statement where you replace the sphere by the Eilenberg-MacLane spectrum. But maybe a somewhat more systematic way of doing that is to say that, I mean, we have the homotopy fixed point spectral sequence, which goes from the cohomology of X with values in the homotopy groups of this spectrum here. I mean, the homotopy groups of this spectrum are just the direct sum over G in G, the homotopy groups of the sphere spectrum. And this whole thing converges or conditionally converges to the homotopy groups of the fixed points. Direct sum G and G, sphere HG. And now the point is that these groups, I mean, these are just for a fixed star here, for a fixed star here, right? These are just basically induced representations. So it is a classical result, classical and not too hard to prove result, that the terms here, the cohomology of any group G, finite group G with values in some adjoint representation over some abelian group A. So here we're going to have the homotopy groups of spheres, but this is just given. This is 0 for star not 0. I mean, of course, I guess for a positive star, the negative cohomology is 0 anyways. And then we have that this, here it is actually A, star equals 0. So in degree 0, it's always the invariant. So this reduces it to the statement I was just alluding to about the regular representation over the integers. And this is not a hard result. Well, but from this result, you immediately see the homotopy fixed point spectral sequence degenerates and gives the result. I guess we have a map, and then we see that this map induces an equivalence. Okay, so, but of course, I mean, this statement basically is the version of the same version here where I replace the sphere by the Eilenberg-MacLane spectrum HA. So in some sense, my proof reduces the statement to itself, but this is a statement in classical group cohomology. So, okay, good. So that's the dualizing spectrum of a finite group. So the dualizing spectrum of a finite group is just a sphere with a trivial action. So I guess maybe let me say that. So this means dg is just sphere, but with a trivial action, triv. Right? Because under this equivalence, the action is the trivial action on the sphere. Right. Okay, so good. So that is the case of a finite group. And what about if G is a compact Lie group? Compact Lie group. Then we have the following theorem. And I mean, in this form, I think this theorem first appeared in work of Klein. I mean, of course, because he was the first to define the dualizing spectrum. But really, this depends on, I guess, this is really a form of Atiyah duality or Pontryagin duality, or Poncaré duality, and I guess uses the version of the Pontryagin Tate construction and has appeared in equivariant homotopy theory long before. But anyways, it's a nice theorem. So what does the theorem say? It says that we have that the dualizing spectrum of G is actually sphere to the G. Where, what do I mean by that? So G is the Lie algebra. Little g is the Lie algebra of G, where, and in general, and I guess maybe I should make a double slash, it's the spectrum, where in general I mean by, if I have a vector space, I mean sphere to a vector space is just defined to be the suspension spectrum of the one-point compactification of V. So that's so that if I input here Rn, then I get the n-sphere spectrum, the n-fold upshift of the sphere spectrum. And I mean, this is obviously a functor, and so this gives you this dg as a spectrum, and of course I wanted to have a g action. It's a spectrum with a g action after all, and so the g acts on g by the adjoint, representation. Right, so big G acts on little g by a conjugation, or I mean the adjoint representation, and that gives you an action on this spectrum, and that's the statement. The dualizing spectrum of a compact Lie group is the adjoint representation of the Lie algebra. And as an example, we can look at the Lie group, the torus, the one torus. So we can look at the Lie group T, by which I just mean U1, or I mean S1, the circle group. And so, but here as a Lie group. And then I get that the dualizing spectrum of T is just a sphere to what is the Lie algebra of S1. It's just the real one-dimensional vector space S1. But the point is, because this is an abelian Lie algebra, the adjoint representation is trivial, or because it's an abelian Lie group. Conjugation action is trivial, so this is actually S1 with a trivial action. By this I always mean the trivial action. Okay, so it's just a one sphere, like a shift of the sphere spectrum concentrated in degree 1 with trivial action. That's what it is here. Okay, so now we understand the... And in fact, of course, you see that my first claim about finite groups is in fact a special case of that. Because for a finite group, the Lie algebra is of course 0, so that this is just going to be the sphere spectrum with a trivial action. Okay, so that settles these cases, but there's another very important case, which is assume that the space BG is homotopy equivalent to M, maybe with a point M0, where M is a closed smooth manifold. Really, what I'm going to say works also for topological manifolds, but let me not, I don't want to go into the microtangent bundle. Okay, so if M is a closed smooth manifold, for example, if G is the integers, then BG is just S1. Right, the classifying space of G is just S1. And I mean, this should not be confused with the last example. Here G is the integer, so BG, the classifying space, is S1. Or more generally, in fact, I can just take like any closed manifold M with a base point M0, and then I let G be omega of M. Right? We've seen actually, in fact, that every group is omega of a space, so can just sort of translate between the group and the classifying space. So for any closed manifold as a group, that this is the case. And then in this case, we have the following theorem. And this is actually Atiyah duality. Just a way of reformulating that. So let me maybe not credit this, because again, this appears in this very nice paper of John Glines, but somehow, yeah, this is certainly much older in some sense. We have that DG, the dualizing complex, is actually the following spectrum. So it's going to be a spectrum with G action. Let me just first give you the underlying spectrum. The underlying spectrum is just a sphere to the minus the tangent space in here. And what I mean by this minus, I guess we've just defined the representation sphere for representations, but of course you can also define the representation spheres for negative representations by just taking the inverse of the sphere, right? In spectra, the sphere is invertible, so we can just shift down and up. And so you can also do that for virtual representations. And that's what we do here, and this is the tangent space of M at the base point M0. So if we ignore, this is just a sphere spectrum in minus dimension of the manifold, abstractly, right? This is just an n-dimensional manifold. If n is the dimension of my n-dimensional vector space, if n is the dimension of my manifold, and then this is just a sphere concentrated in degree minus n, right? That is possible in spectra. You can just shift down by n. Okay, but maybe the question is, how does this carry an action of the group, right? Because this is just a spectrum, and so as a functor from BG, which is equivalent to M into spectra, this sends then it's a point little m in M to the spectrum sphere to the minus tangent bundle in the point M, a tangent space in the point M. And because the tangent bundle is a bundle, so it depends continuously on the point in the base, you can see that this depends continuously on M, or said differently, this defines a functor from M to spectra. Okay, and that is what the dualizing complex is in this case. And here you actually very clearly see that for this is actually, of course, if I want to translate back this into an action, then I would just say, well, it's such a functor. So in other words, omega m, which is just endomorphisms in the infinity groupoid M of the unit, act on that vector space up here. But writing down the action up here isn't very natural. I don't know a very easy, natural way of doing that, except for maybe talking about some homotopy coherent monodromy. So for this example, this perspective of functors from M to spectra is actually very important. Okay, so that is the statement, and admittedly, I mean, one has to think for a second how one precisely makes this into a functor, but I don't want to go into that too deeply at the moment. It's just somehow the idea is to make the fiber-wise one-point compactification of a vector bundle into a functor from the base. Okay, so that is the theorem. And let me explain some consequences. But before I do that, I want to make one remark which is related to what I just said in the previous example. One can define for any space X in place of Bg a dualizing spectrum, a dualizing spectrum dx, and that is now going to be a functor from X into spectra, aka a parameterized spectra, for those who know this language. For example, by defining this functor on connected components. So X as a space just decomposes, and I mean, remember a space meant something like Grant complex, so it decomposes into a disjoint union of connected spaces, which are then all of the form BGI for GI some group objects, and then on BGI it is DGI. Right, so in order to write down a functor from this disjoint union to spectra, I just need to give you a functor on all of these components, each of the components, and then I'm just going to give you DGI on BGI. And I guess there's also a more direct way of doing that, where you somehow work with functors from X to spectra the whole time in parameterized spectra, and then you write down the formula I have given you for the dualizing spectrum in terms of homotopy fixed points in terms of a limit. So, I mean, this would involve some operations of parameterized spectra, which I didn't want to introduce, but it's exactly the same formula. Everything works the same. It's just a sort of slightly different perspective on the thing. Whether you think of this as X as a space, or you want to think of the group G. Okay, and also this terminology is maybe a little misleading, because I either write DG or DX, and sort of X is either a space or a group, so somehow group canonically gives rise to a space BG. Okay, so that is my intermediate remark, and now let me tell you the main reason we introduced that. And as a preparation, we need the following construction. So we're going to assume that C is a stable infinity category, which has all limits limits and colimits. And actually, I mean, this is for pieces of what I'm going to do, this is going to be too strong of an assumption. Sometimes you'll only need colimits, sometimes you don't quite need stability, but let me just make this assumption. This covers all the cases we care about in this lecture course and the TC course, and will be good enough. So if you have an infinity category, stable infinity category which has all limits and colimits, then for any E spectrum and X in C, there's an object E tensor X in C, which I'm going to explain what it is in a second. But this is like an action of the category of spectra on C. So C is a sort of module over spectra. So it's tensored over spectra. That's another way of saying that. And but I will only need the spectrum. And how is this defined? Well, defined as follows. Defined such that I'm not going to characterize this for a fixed E, but I'm just going to say that blank tensor X is a functor from spectra into C. And I could actually say this is also a functor when I let the X vary, it's a functor from spectra across C to C. But let's say as a functor from spectra to C such that the following holds. First of all, it sends colimits of spectra to colimits in C. And secondly, for suspension spectra, it's just what we already know. So the composite from spaces into spectra, suspension spectrum, and then post-composition with our functor blank X into C is given by the functor, well, which takes a space, let's call that little e, well, this is terrible notation for a space. What is good notation for a space? M maybe? M, and sends it to M tensor X. And that was defined to be the colimit, the constant functor on X over M. Right? And so in other words, I have that if I take the suspension spectrum of my space M and tensor that with X, then this is the same as M tensor X. And this makes sense as defined through the colimit. And I mean, it's basically clear that this functor is uniquely determined by saying what it does in suspension spectra, because remember that every spectrum was a colimit of desuspensions of suspension spectra. And from the preservation of colimits, you first of all see that it has to commute with desuspension, because it commutes with suspension, and suspension is an equivalence, as both categories are stable. So here you crucially need C to be stable. And then you see that you can extend this. For this, actually, in reality, you're using some universal property, which is somehow related to our construction of this mesh product. So I'm not going to prove this. I'm just going to give you the construction. And this is completely functorial, as in both variables. And in fact, it can also be characterized as being adjoint to the mapping spectrum. So in the last video on the TC course, Achim has introduced mapping spectra, and this can also be characterized by saying that maps out of this guy into any object is the same as maps from E into the mapping spectrum. That's maybe then closer to a tensoring, if you know what that is in ordinary category theory. Okay, so that is anyways our construction. And now we want to define the so-called norm, which is one of the major objectives of today's lecture. Okay, so G is going to be a group object again. group like E1 space in spaces, and X is going to be any object CBG. So C is a stable infinity category set that has all colimits and limits. So we define the norm map, the additive norm map, and this is going to be a map from dg tensor X, homotopy orbits G, into X homotopy fixed points G. And this will be denoted norm G. And I'm going to give you this map in a second, but let's first think about what this is. And here I should maybe write tensor over the sphere. So what we do is, has a G action, this has a G action, and if we tensor them together, we equip that with a diagonal G action. So that has a G action, and then we take the homotopy orbits for this G action. And then it's a map from here into here. It's in fact a natural transformation, natural in X. And let's see how this is defined. Namely as the composite So let's write down what the left-hand side is. So the left-hand side was by definition the suspension spectrum of G. And then we tensor this over the sphere with X. And I should have actually put here homotopy fixed points for G cross 1. And then we take the homotopy orbits for G. And I want to be a little bit careful as to how these things act. So remember, the remaining action we had on this guy was just by 1 cross G. So let me write this as 1 cross G. And then in order to make sense of that, we have to let X is considered as a G cross G spectrum where, well, I guess 1 cross G X trivially and G cross 1 through the G cross 1 X trivially and 1 cross G through the given G action on X, i.e. our functor Bg cross G, this is a side note, Bg cross G goes through projection 2 Bg, and then here we go to our category C, that's X. So that's the way I want to consider X as a G cross G spectrum, and then you see this tensor product is again going to be a spectrum for 1 cross G, right? Because this is still a 1 cross G spectrum, and then this is a 1 cross G spectrum, and then I take the homotopy orbits. Okay, and so what I can do is the following. So here I've taken homotopy fixed points, and that is tensoring with X. And what I can also do, of course, is I can take the combination. I would like to pull tensoring with X inside of the homotopy fixed points. And this is because, of course, on this I act trivially. So this is just interchanging tensoring with this homotopy fixed points. And I can't. In general, this will not be equivalent. So in the best possible scenario, I would say that this is equivalent to this guy. And then taking homotopy orbits down here. But it's not. But doesn't matter, there's always a map from here to there by the universal properties. This functor tensoring with Sx does not quite commute with taking homotopy fixed points, but there's always a canonical map into the limit, right? So always, like whenever you have a functor which does not necessarily commute with limit, there's going to be a map from f of the limit into the limit of f of the diagram. Okay, so this is the canonical map, and then now I have two actions here, and I can actually also interchange these two actions, because there's always, like, colimits don't quite always commute with limits, but there's always a canonical map So the Collimate limit interchange map. So this is a functor into sigma infinity plus g tensor over the sphere X. And I have first now take the homotopy orbits 1 cross g, and then I take the homotopy fixed points g cross 1. That's another instance of this commuting limits with a functor or dually colimits with a functor. And okay, so now I have this guy. And now at this point, what is this inner guy? So, well, I mean, it's just a homotopy orbit of g acting on this guy. And because the way I installed my g action, I have that this g actually acts on both coordinates. But the claim is that this is equivalent as a g object to just the thing where I only act on the left coordinate, and then I take homotopy orbits, I'll only get x. So the claim is, and I want to leave this as an exercise, that this whole thing is canonically equivalent to x upper hg. And so what you have to do for this exercise is you first have to think about why this is equivalent to x, this whole homotopy orbits. And then you have to think about what the residual action of g cross 1 is on this x. And the claim is this is just the action I have started with. And this has to do with a specific form of the equivalence of this guy to x, which I want to leave as an exercise. The keyword here is to use a so-called shearing equivalence. Right, so by definition, the norm is just the canonical limit interchange map that we have under some sort of canonical identifications. But nevertheless, it turns out that this is a highly non-trivial and very important map. So let's work out what that is in some examples. Example 1. So, well, if G is finite, then what do we have? Then the norm is a map from, I guess in this case we have, I mean x, and x is going to be always throughout, say, an object with bg. And then I guess we have that this is the dualizing spectrum g, hg, and we have seen that actually the dualizing spectrum for a finite group is just a sphere. Right, and I guess I wanted to write this the other way around, so sorry, I wanted to write it like this. Tensor over x. And by the way, in my last formula, of course, I just wrote the sphere here to this tensor to make clear that we're just tensoring underlying. This is not meant to indicate that we're tensoring in the category of spectra. This was just a general tensor we introduced. This was just indicate to say that we, as G object, it's like the underlying tensor. Maybe this was a little unfortunate, I now realize, as a terminology. Hope this didn't create too much confusion. Okay, so for a finite group, we have seen that the dualizing spectrum is just a sphere with a trivial action, though this is just equivalent to Hg. And one has to be a little bit careful. This equivalence, this depends on the choice, the equivalence between dg and s. So this depends on that. And then, of course, we have the norm here. I guess the norm really canonically goes from here into x upper g. So what I'm saying is for a finite group, the norm is just a map from the homotopy orbits to the homotopy fixed points. And again, be a little bit careful with the identification. So for example, if C is the category of spectra, say, or I guess a similar example would work for the category of chain complexes, we can look at the case X is an Eilenberg-MacLane spectrum of an abelian group, and I mean M is an abelian group with G action. And then this map is a map from xm hm lower hg to hm lower hm upper hg. Well, but these are just the homotopy orbits and these are the homotopy fixed points. So these are canonically concentrated in non-negative degrees, and these are canonically concentrated in non-positive degrees. So as a result, every such map will factor through pi naught of this, which is just the Einberg-MacLane spectrum on the orbits, the co-invariance of G acting on M in the sense of abelian groups. And then pi naught here is actually the fixed points for this action. So it's H M upper G. And the claim is now, so this whole norm map here is induced from a map like this. And so this is induced or equivalent from the map, the classical norm map. Norm or transfer or map from the co-invariance to the invariance for any abelian group with G action, which just takes the class of M to the sum over all G translates Gm. Right, that, I mean, this is a classical map. It's easy to verify that this gives a well-defined map from the co-invariance into the invariance. Okay, so that is the norm in this example. And how does one see that? Well, this follows from the claim that for general X, but still G by a finite group, the composite so I can always consider the following composite, where I go from X into the homotopy orbits of G acting on X, right? This is just a canonical map from X into the Collimate structure map. And then I have the norm here. And then I go to X upper HG. And then to X with, again, the canonical structure map of the limit. That this composite is given by the sum of the maps multiplication by G, which are mapped from X to X, right? So X has an action by G as a spectrum, and so for every fixed element G in G, I have the multiplication by G map from X to X, and the claim is it's the sum of all those maps. And this basically follows from the identifications that I've done, and I want to leave that as an exercise. So I think this exercise is a little tricky, but at least I think you should somehow go through the identifications, and at some point you might sort of believe some statements, as in like analogy to ordinary algebra. I mean, this can also be made completely rigorous, of course, but I'm just saying somehow at least going through the identification and seeing how this is true is a really good exercise. So you have to actually think a little bit about, this is why I sort of said over there that the identification of the dualizing spectrum is an input into that. And then, going through all the identifications and the canonical map we've made, the claim is that one can see that here. Okay, good. So that is this case. So you see the norm that we've talked about, the homotopy theoretic norm that we've introduced for any group object in space is just a generalization of the norm that we had for finite groups. And it's very surprising. It, for example, also works for non-finite groups. But it even works for any arbitrary topological group or E1 group objects, which I find very surprising. And for example, for compact Lie groups, so for G equals S1, U1, the torus group, we get a map from the suspension of sigma HT, which is just the same as taking the dualizing spectrum of T, tensor X HT. Why is that the same? Because remember, the dualizing spectrum of T was just given by the sphere in degree 1 with a trivial action. So we can just pull that out to become a suspension. And then we just have a map into X upper HT. So that's what the norm, or I mean this map is actually in homotopy theory also called the transfer, the as one transfer. And I mean, I guess at this point we don't really know whether or not this is a non-trivial map, and actually it is non-trivial, it's highly non-trivial, it turns out. And of course at this point we can't quite sort of understand that map because I've used some implicit identifications of the dualizing complex in this case. So unfortunately we can't quite say what it is in terms of that. We'll later see how to identify that in terms of profinite, I mean in terms of transfers for cyclic groups of order n and some, at least after profinite completion. Okay, but now to an important theorem about the norm map. Which is the following assertion. The norm map from dg tensor x hg x upper g is an equivalence provided that one of the following conditions holds. One, BG is a finite CW complex. Right, and by this I mean, of course, BG is only a homotopy type. I mean, it's homotopy equivalent to a finite CW complex. It only has finitely many cells, or said equivalently, it's finite as an infinity category. BG is an infinity groupoid, and it's finite as an infinity category. Or the second condition is that X is induced. That is, X is as a G space, as an object with G action, it's equivalent to sigma infinity plus G tensor Y, where G acts on sigma infinity plus G. So G acts on this tensor product by just exactly acting on this coordinate. So that's what I mean by induced. It's freed up from a non-equivariant spectrum, non-equivariant object, it's freed up to an equivariant object. Okay, and why is this true? And this is actually very easy now, given our definitions, at least the first part. But nevertheless, I call it theorem because I'll tell you what this has as special cases in a second. But I mean, the first part is that, I mean, in this case, all limits, colimits, all limits in the interchange maps are finite. Right, so if you remember how the norm was defined, we had to interchange functors with limits. And so all these functors were exact, so they commute with finite limits. So in fact, they commute with limits indexed over BG. So recall that a finite limit in an infinity category was just something, a limit indexed by a finite infinity category. BG is a finite infinity category under this assumption. So the limits and colimits that come up are finite, and so all the interchange maps are equivalences. And that proves one already. And for part two, you have to see that two is much harder actually, but somehow if you're induced up, then homotopy orbits, I mean, somehow we've seen before this lemma for finite groups that then there was no group cohomology, and somehow in the induced case, the colimits and limits are still close enough to finite. I mean, so somehow it's not the indexing category is finite, but the limit itself has a vanishing line. And I'm not going to get into that. I mean, so I'm not going to prove part 2, but part 1 is completely easy given the definitions. And why do I think this is like a sort of actual deep result? To see that, let's look at an example. So what I want to do is I want to let BG be a closed manifold as before, and I want to let X. I want to let C be spectra, and X is going to be HC with a trivial action. It's a trivial functor from BG. Maybe I call this manifold M. Okay, so what do I get? So in this case, the norm is the map from X tensor DG tensor X HG into X upper HG. And let's work out, what these objects are. This is always the case that the norm is a map like this. And we know it's an equivalence actually by the first part of this theorem. So let's work out what these objects are. So this is just HZ to the BG. Right, the action is trivial, so this is just a mapping spectrum. Maps from BG into X. Right, that's the mapping spectrum. And what are the homotopy groups? The homotopy groups of that, homotopy groups of HZBG are just given by the cohomology minus star of the manifold M with values in Z. Right, that's just how the cohomology is defined in terms of a mapping spectrum. And so that's the target of my map. And what is the source of my map? The source of my map is just, I guess, just working out what it is. We've just sort of input the fact that by the theorem of Klein's that we have had before, or I guess the more classical Atiyah duality style result. So this is just the sphere to the minus tangent bundle of M, right? T, maybe Tm. Let me write it like Tm, and it like sort of varies as the base point varies. That's the way it's a functor from M to spectra. And then I tensor that with Hz. Right, and then I want to take the homotopy orbits. But what is that? This is just equivalent. Of course, this is just a sphere. So if n is the dimension, this is just a sphere sitting in dimension minus n. So this is just a copy of Hz shifted down in degree minus n. But this has a non-trivial action of G, and I take the homotopy orbits of G. And so the question is, what is this action that I have, right? So this varies as I wander over my manifold M. And so what happens is, you see, from this identification at every point P, this is just given basically by the homology of the sphere of the tangent bundle in this point. This is of course equivalent to choosing a neighborhood, like a normal neighborhood, where the sphere, like the tangent bundle, is equivalent to an open neighborhood, and then taking away, taking the homology relative to the base point. Right, so this is actually literally just, if you think it through, this is just exactly, the homotopy groups of that are just exactly given by the homology of M with coefficients in the orientation cover. The usual sort of local system. Or, the orientation cover is just defined to have, like, at every point to be the homology of a neighborhood relative to that point. Or neighborhood take away this point. Okay, so, right. So here you see that our map now on homotopy groups is a map from homology of M with values in this into the cohomology of minus star. And actually I should have been a little bit more careful. It's actually not the homology of that, but it's the homology shifted down by n, right? Because we have this shift down. So it's a homology shifted down by n of M with values in here, and it goes to the cohomology of M. And so what is this? Well, this is Poncaré duality. Carré duality. Well, that's just the fact that homology, and I guess, I mean, here we get really like homology with coefficients in the orientation character, because, I mean, I didn't assume my manifold was orientable. So if my manifold is orientable, then this is trivializable, this twist. So, or actually an orientation defines the trivialization of this twist. So that in that case, I just get classical Poncaré duality from homology being isomorphic to cohomology. And so in that sense, this theorem encapsulates a Poncaré duality, but of course, I don't want to trick you into believing that this is a proof of Poncaré duality, because the real work, of course, I mean, this is just an abstract, easy statement. The real work lies in this identification of the dualizing complex with the sphere of the negative tangent bundle. Right, so this is really, I mean, as I said, this kind of encapsulates like Atiyah duality. So it's basically the same, I mean, the sort of Pondriagin-Thom style proof of Poncaré duality, but so I'm not claiming this is a new proof of Poncaré duality, but what I claim is it's a very nice formalism and a very nice way of thinking about that norm as being a sort of, for BG finite, this is just a Poncaré duality map. So they immediately see that also it's a highly non-trivial map, of course. This map is far from being trivial in general. If I replace Hz by any spectrum, we get Poncaré duality in arbitrary cohomology theories. Or I should say cohomology slash homology theories. It compares twisted homology with cohomology. And I did not have to assume for the norm to be an equivalence. Of course, I mean, I only needed to assume that X was a finite BG was a finite ZW complex. So if X equal BG is a finite CW complex, the norm equivalence X tensor dg or dx colim lim. I guess maybe we can see is a generalized version of Poncaré duality. Version of Poncaré duality. So it goes from something like you could call homology of X with values in the dualizing spectrum X, and it's isomorphic to minus cohomology of X. And maybe I should say minus cohomology and sort of maybe should sort of allow my spectrum to be E, I guess. I could formulate an ordinary homology. And you see the point is that in general this dualizing spectrum will not be, I mean it's actually going to be a finite spectrum, but it will not be, I mean under my assumptions, but it will not be concentrated in a single degree in general. So this tells me somehow that cohomology is isomorphic to a combination of twisted versions of homology which are sort of concentrated in different degrees. And that is similar to how Serre duality and dualities in algebraic geometry, Verdier duality work in general. And of course, if dx is actually a parametrized sphere, which under our equivalence to dg, so by which I mean dg is just a sphere as an underlying spectrum, sphere in some degree as underlying spectrum. This ends up being equivalent to saying that X is a Poncaré duality space. Carré duality space. For those of you who have seen this notion, so all others can just take this as a definition. Space is called Poncaré duality space, and a finite space called Poncaré duality space if the dualizing spectrum is just a sphere underlying with a possibly non-trivial action. And in this case, from what we've talked about, the norm immediately gives us an equivalence between a homology of X with values in the homology of the dualizing complex into cohomology. Okay, so that's a sense in which the norm is a generalization of Poncaré duality, and it can also be characterized by a universal property as follows. This is also a theorem of John Klein's. In a different paper though, which says that the transformation, I mean, this is not quite how he formulates it, but still a theorem. So the transformation blank tensor dg, I guess I wanted to write it, dg tensor blank hg to blank upper hg, where you input an object with a g action. I mean, both are functors in X. Exhibits the functor dg tensor blank lower hg as the universal functor over the functor blank upper hg, so the best approximation of hg from the left, which preserves colimits. Right, as a functor from in the variable blank, where blank is an object with a g action. i.e., there's also a name for this universal transformation. It's called the assembly map. So the assembly map is basically this natural transformation, but of course the natural transformation in particular also contains its source. So one should always think of this as a universal property for the functor together with the norm. Well, that's a universal property. And in fact, there's two remarks that I want to make about this. I mean, the first remark is, well, if BG is finite, then the functor blank upper HG already does preserve colimits, right? Because BG is a finite limit, so it commutes with all colimits. So as a result, you see in this case already the assembly map is also the identity. So that repackages the claim that for BG finite, this is an equivalence. So it's the identity naturally in this case under, I guess, the identifications. That's the first remark I want to make. And the second remark I want to make is that this also, note that this uniquely determines dg. And why is that? Of course, this is just, if C is the category of spectra, then you see these are functors from spectra BG to spectra. But in general, I mean, if I start with my homotopy fixed point thing functor, and I approximate it, you can abstractly show there's an approximation by a functor which preserves colimits. And then it turns out that every functor which preserves colimits from here to there, that's a form of monoidal theory, is just given by any spectrum tensor blank homotopy orbits. So in fact, the category of colimit preserving functors from spectra BG to spectra is just equivalent to spectra with a G action. And under this equivalence, of course, this functor corresponds to dg. So from saying this functor as a functor completely knows about the object dg. So this can also be seen as a universal property for the object dg. And in fact, what I just said is basically close to a proof of the theorem of Klein's. Why is that? Because, well, I mean, in general, you can just sort of give a general form for assembly maps. And it turns out, in the case of spectra, this gives you the assembly map, and for general categories you have to use this claim that induced, this functor vanishes on induced spectra to see that this general form of assembly simplifies a little bit. Because C to the BG might have more than one generator. But this is roughly the idea. So this is not somehow it's a really neat observation and somehow really puts everything, in my opinion, in the correct context. You have like a universal property and this functor is uniquely determined. Okay, so now I've spoken quite a bit about the norm map, but I really claimed to get to the Tate spectrum. So what's the Tate spectrum? Or the Tate construction? Definition. For x in C to the BG, we define the Tate spectrum as, well, x to the Tate G is just defined to be the cofibre of the norm map. And here G is again a general E1 group. Very often in the literature you'll only see the definition for finite groups or compact Lie groups, but this is just completely general. Just defining it as a cofibre of the norm map. Or the Tate construction. I should not say Tate spectrum, since I guess X was not a spectrum with G action, but an object with G action. Example. Well, the first example is if BG is finite. And that example is boring because then x Tate G is 0 for all x. Well, that's just because we've seen before that the norm is an equivalence in that case. So that is a boring case of the Tate construction. This also sheds some light, I believe, on what the Tate construction really is, because somehow if we buy that fact that the norm map is a generalized Poncaré duality map, then you see that the Tate construction is exactly the failure of Poncaré duality for the space BG, right? So you actually see that this Tate construction is a measurement how badly Poncaré duality for the space BG fails, or how much cohomology differs from a twisted form of homology. Okay, so that is the first example. So what about for G finite? So the only case where we really understand the norm, I guess, besides the Poncaré duality case. And I could have included also in one that, of course, if X is induced, then we've also seen that the norm is an equivalence. So for induced objects, the Tate construction also vanishes. But for G finite and X of the form HM, again, Einberg-MacLane spectrum, where M is an abelian group with G action, or in other words, a module of the group ring, we have that HM Tate G is just a cofibre of the norm map. And this was just HM lower HG into HM upper HG. Right? So that was kind of our norm. And it's a cofibre of that. And the homotopy groups are given by, so I guess the homotopy groups in degree star of this HM Tate G are just given by, this is classically what is classically called Tate cohomology. This is a thing that Tate introduced. Tate cohomology of G with values in M. And I want to leave it as an exercise for you to work out what that is in terms of classical invariants like homology, cohomology, and maybe the co-kernel and the kernel of the norm map. So roughly speaking, what you have to do is you have to contemplate that this sits completely in non-positive degrees, this sits completely in non-negative degrees, and so being the cofibre, there's a long exact sequence, and you can just work out what that is. So the homotopy groups of this guy are group homology, the homotopy groups of this guy are group cohomology. So that is classical Tate cohomology, and this is how this generalizes classical Tate cohomology. And I should have maybe said, I could have as well carried out that whole example in the category of chain complexes. Then I would just sort of consider the object in dz, in the derived infinity category of the integers, just m concentrated in degree 0. And then because the functor from the derived category to spectra preserves limits and co-limits, it also basically preserves everything I did here. So I could have carried out this just exactly in the derived category of the integers, if this helps you in terms of resolutions. Okay, so that's this exercise. And now I want to finish this lecture by some structural properties of Tate. But let me maybe also say that, for the case that the group is not finite, but still has some niceness properties, this construction was known as Farrell-Tate cohomology. And I guess we have this basically defined now for arbitrary groups, but to the price that it becomes very inexplicit. And of course, again, I could have just defined the Tate construction for space instead of in place of G. So replacing Bg by an arbitrary space, I could define the Tate construction as well as a cofibre of the norm. But okay, so here's a theorem about the formal structure of that. So assume that C is a symmetric monoidal infinity category. Such that the tensor product commutes with co-limits in both variables separately. Then the functor blank Tate G from C upper Bg to C. So I guess I was a little bit sloppy. I said at some point I sprinkled in the fact that everything I did was natural. So that Tate actually is a functorial in the object X. And so the claim is that admits a Lax symmetric monoidal structure, which is actually even unique. Unique Lax symmetric monoidal structure such that the transformation from the homotopy fixed points into the Tate construction, but there's such a natural transformation because Tate was defined to be the cofibre of the norm, and the norm had as target homotopy fixed points. So just the canonical map into the cofibre is this map, and this is natural, such a natural transformation admits a refinement to a symmetric monoidal transformation. So here I'm using that the homotopy fixed points admit a Lax symmetric monoidal structure. Achim has explained that, or at least stated that in the previous video. One way to see that is just that this is right adjoint to the constant functor. And right adjoints to strong symmetric monoidal functors always admit lag symmetric monoidal structures. And so this is going to be a lag symmetric monoidal transformation. And why is that useful? I mean, this has the following corollary. Corollary. If A, and by the way, I should have said this here, of course, inherits the pointwise tensor product. It's just the, object with a C action in G action in C are just tensored by underlying tensor product and then giving the diagonal G action. That's the way I equip, this is a pointwise tensor product, in other words. And because this is a pointwise tensor product, it turns out that if I have a commutative algebra in C to the BG, it's exactly the same as a commutative algebra in C with a G action. In other words, A is a commutative algebra in C, and G acts on it through maps of commutative algebras, E-infinity algebras. Then HTC TG is a commutative algebra. Right, because lag symmetric monoidal functors send algebras to algebras. And of course, I could have said En algebra here, En, and then this would also be an En algebra. And moreover, the map is a map of commutative algebras from the homotopy orbits to the Tate construction. And that is the last thing I want to say. And for those people who have done the previous exercise, at this point, it's very nice to think about. This is actually kind of surprising fact. Because if you've done my last exercise, then you know that the Tate cohomology has to do with group homology and cohomology. And this tells me that if I combine group homology and cohomology in this funky way together, then this inherits a ring structure. I think this is kind of surprising, but it kind of encapsulates the cup product on cohomology and the module structure, the cap product letting cohomology act on homology. Okay, thanks very much for listening, and see you next time.